Wanted to give you a brief rundown on the Arduino. We're going to cover basic Arduino hardware, digital I/O, analog I/O, and serial communications. Testing, 1, 2, 3. Let's see if we can get this to work. So we've got basic I/O lines up in here, which can be used for input and output for the transmit and receive lines. Can be used for serial interrupts, or can be used for pulse width modulation, or can be used for output, which can drive our LEDs. And we've seen examples of all of this in our laboratory. This little area in here is what they call a low dropout regulator, 5-volt regulator. When you put 9 volts into a DC power jack, this little regulator will make sure it pumps out 5 volts regulated. Got another low dropout regulator. That one gives us 3.3 volts, and we can have access to these things right here through these pins. Here's the 3.3 volt and the 5 volt, and we got 2 grounds to work with, and a voltage in, which can be used for a to D converter reference. We've got 6 different analog inputs, but in fact they're all sharing one analog to digital converter. So if you have to use all of them, you're generally speaking going to suffer in terms of your rate at which you can sample. There's a 16 megahertz crystal and a little fuse in here, and then a USB jack, which can be used to drive the Arduino directly. There are transmit and receive lights, and there's a separate pin 13 LED. So when you assert pin 13, this little LED, this is a surface mount device, that's going to light up. This little USB to serial IC chip comes in, well, at least 3 flavors. The CH340G, for which you might need a driver. The SI2102, also you might need a driver for that. And then there's a standard FTDI chip, for which licensing fees must be paid. And there's an Atmel chip available as well. So probably 4 common variants, depending upon which one you have. And you really have to look very carefully to see what variety you've got. So let's take a look at some of the things you need. Well, of course, we know we need an Arduino IDE to install. You won't have to install it if you're using lab computers, but if you have a computer at home, of course, you've installed this already. You must select your board and serial port, and make sure you have the right serial port and the right board, or else you will not be able to upload. And you've tried a Brink example already, so that's good. And typically we saw the loop and the setup as 2 separate areas. Setup was executed once at the beginning, and then we executed a loop, an indefinite loop, or an infinite loop. Serial ports on a Windows computer are probably called COM1, COM2. On a Mac, they're called something else, generally /dev/ttya. And here's what happens when you select an Arduino Uno from the board section. So you've got to have the right board and the right COM port, or else things just don't upload properly. And then once you write your sketch and you do your compile, and I like to call it a sketch, it's really a program, you've probably done an upload. We see a transmit receive flash, and then it automatically does a reset and runs the program. So that's a part of the charm, I guess, of running Arduino code. Every time you do an upload, it resets the processor. So then there's this thing about input and output, and here's where things get interesting for Arduinos. We've got enough, I'll call it robustness electrically to be able to handle driving things that require some current, and we can also sense some stuff. And each time we add another sensor and another lab, we're creating a sense, in a sense, a kind of building block, right? These are the bricks by which you can build larger systems. So when we looked at digital I/O, we saw things that were essentially modulating the duty cycle of the output in order to be able to obtain an approximation to a continuous voltage. We ran this through a low-pass filter, and we did this because we didn't have a digital to analog converter. But it's not all that hard for us to build our own digital to analog converter, and in fact, Tinkercad and the various other simulators enable us to do that. So what happens with the ports is they have a mode. they're either set to input or output. And because they're I/O ports, you have a digital data direction register. You set up the pin, and then you set it up with the input or the output, which are literals that are embedded inside of the code. And if you've got an input, you can read from the pin, and if you've got an output, you can write to the pin. And it looks like we can get about 40 milliamps of current, which is pretty decent for a little microcontroller. So that's what makes the Arduino kind of a robust microcontroller, because you can sink 20 milliamps of current. That's not a lot, I know, but it's enough to be able to get things to run, especially small servos and small stepper motors. After 40 milliamps, you need something else, like a Darlington transistor, to make things go. So here comes the blink sketch, and you think about, how much current can I sink? And the answer is, well, 40 milliamps. And how much current does this thing need? Well, you can take out a calculator and do a quick computation. Typically, we use about 220 ohms for a current limiting resistor for a 5-volt device. And because we know that E equals IR, and because we have 220 ohms, we can take E, which is 5 volts, and divide by 220, and we can get a current. And if we do that, 5 divided by 220 should give us something quite reasonable and close to what we're allowed to use, and the answer is 0.022. Multiply that by 1,000 and you'll get 22 milliamps. So if you put a 220 ohm resistor in there in the output in series, it'll current limit you to 22 milliamps, which is enough to get the LED bright. And you want to limit the amount of current the LED will sink, because in theory you could blow out the LED, although probably 40 milliamps won't blow out most LEDs. They'll make them pretty bright though. So now we've got a mechanism for outputting binary signals and for inputting binary signals using our digital outputs and inputs. Moreover, the binary signals, if it's pulse width modulated, can give us continuous approximations. And we have inputs that are analog. So we can have an approximation to an analog output, and we have an analog input with the 0 through 5 ADD converter ins. And so here's the little example with a 220 ohm resistor. And now we've got our little LED in series with us, and we can use our Arduino to sense the push button and then proceed to make the LED light. So here comes this idea about sampling, we'll say. And what we're doing with sampling is we're quantizing in voltage, and we're sampling in time. So those are two things that go on when you do an ADD conversion. And you can kind of see what happens if you wait too long before you do a sample. You get a very rough approximation of the sine wave, whereas if you sample a little bit more frequently, the sine wave comes out quite a bit smoother. And this is the difference between sampling at 44 kilohertz and sampling at 192 kilohertz for a 10 kilohertz reference analog signal. So that kind of gives you a basic idea as to why sampling is kind of important. 44.1 kilohertz is actually the CD, that is compact disc, sampling rate. And you can see it's not really a very good approximation to the 10 kilohertz reference analog signal. And 10 kilohertz isn't even the top frequency. We can go to 20 kilohertz. So much better if you have 192 kilohertz, the so-called DVD audio. This is what happens when you get a 3-bit analog to digital converter. You have effectively created a quantization noise level. And that quantization noise level is 2 to the 3 divided into the total number of volts. If it's 1 volt, 2 to the 3 is 8. So basically you're going up by 1/8 of a volt, which is 0.125, I think. Let's just check. And yes, indeed, that's true. So if we go up by 0.125 volts each time, you can see the quantization levels are quite coarse. And this doesn't even speak to the issue of sampling rate. This is quantization levels. So 3-bit digital analog conversion is not really very good. Here's one way you can implement a digital to analog converter. They call this an R2 ladder. R2 because you have a single resistor with a single resistance that you repeat, and then you have another resistor that's twice that resistance, and you just need two different kinds of resistors. As the bits go in, you get additional voltages coming out, and typically you'd run this into an op amp or something that would buffer it. So now you've built a kind of 4-bit digital to analog converter, but you've taken 4 bits worth of digital output in order to do it, right? Because look at this digital output. You need 4 pins coming off the Arduino. Well, that's not such a big sacrifice, but a 4-bit digital to analog converter is not that good, right? I mean, think about it a different way. 2 to the 4 might be 16 if you have 5 volts and you're dividing it up into 16 chunks. You're basically giving it each chunk 0.3 of a volt. That's not good. 0.3 of a volt is not a good sort of, we'll say, quantization noise. That's a lot of quantization noise. So here comes the clock signal going into a sample and hold. That's going to sample in time. And then we go through and do an ADD conversion. And what that's going to do is it's going to quantize the signal and give us a digital output. What we'd like to do is have uniform sampling. So here comes our Arduino analog input, and what he's got is a 10-bit ADD converter, which gives us 2 to the 10 or 1,024 different states. So if we think about that, we're dealing with quantization noise of 4.8 millivolts for a 5-volt full range with a sample rate of 10 kilohertz. So what this means to me in terms of maximum frequency I can input into the system, I can put in about 5 kilohertz total. And that's our maximum frequency. And the reason I say that is because you can only go up to as high as 1/2 of the sampling rate on the input signal before you start to get very bad aliasing. This is called the Nyquist theorem. So you've got a problem, right? Because the ADD converter is not that doesn't have that good a dynamic range, and it doesn't have that good a sampling speed. And that's a bit of a problem. So when we think about quantization, we think about the total number of quantum bits, 2 to the n, where n is the total number of bits in the ADD converter. And if we have a 3-bit ADD converter, then we've got 2 to the 3 or 8 different possible levels. And our analog quantization size, let's say if we're going from 0 to 10 volts, is 1.25 volts. That's not so good, right? I mean, if it was 1 volt, it would be 0.125 volts, and that still wouldn't be so good. We've got, we'll say, poor dynamic range in this ADD converter. And then aliasing occurs when you have something that's a harmonic of the sample rate. So here's a 2 kilohertz sine wave being sampled at 1.5 kilohertz. You can reconstruct it at harmonic numbers. So you can have 2 minus 1.5 or 500 hertz as a harmonic, and 2 plus 1.5 or 3.5 kilohertz as a harmonic. And so Nyquist tells us we've got to do our sampling at least twice as high as the maximum frequency in the signal in order to avoid our aliasing. And this is a basic concept in digital signal processing, which is pervasive in all fields. Here's a very fast way to do sampling. It's called a flash converter, and this you can get to run at many gigahertz. And what we're doing is we're using a resistor network, and as the voltage gets to a certain level, the op amp will output a signal, and our little priority encoder will give us a binary output depending upon how high the signal gets. But in fact, you need a lot of little comparators, and unfortunately, it makes for a fairly expensive type of a device, even though it's an extraordinarily fast one. So the flash converter is, a simple operational theory. It's very efficient in terms of speed. It's very fast, but it's kind of expensive. And it isn't necessarily lower resolution as long as you're willing to have enough comparators. So for example, for 8 bits, I need 2 to the 8 comparators. That's a lot of comparators. And if I want 1024 comparators, I better think about a way in which this can appear on a single chip, because I'm not going to wire 1024 comparators. That's too many. Way too many. So here's an architecture that we're using presently inside the Arduino, and this is called the successive approximation ADD converter. And this little guy basically has a DAC in him. And what the DAC does is it uses the comparator to chase down the actual input signal. And so this successive approximation register compares the input signal against the output from the DAC. If it's too low, it counts up. If it's too high, it counts down. After a certain time, it says it's done. And the successive approximation register basically latches. This is a D flip-flop array, and it latches the output of the successive approximation register so that you can have a binary signal that represents the input's voltage. So that successive approximation register, in fact, you can build this. You could build it out of an R2 network and a little counter, or you could build it out of an R2 network and perhaps a comparator and an Arduino. So here's a R2 network that we're using an Arduino with, and that's giving us a DAC. Here's the comparator coming in, and now we can compare the voltages coming into the comparator against what the DAC is outputting in binary. And now we can take the comparator output and put it into pin 8, and then proceed to build our own successive approximation ADD converter. This is already built into the chip, so we needn't do this, but it's interesting to note that we can. So then the question is, what about an analog output? And for that, we can use pulse width modulation. And here we can see how the width of the pulse could be perhaps 23% of the maximum width, and we can get 23% brightness out of an LED. So it approximates the analog output, let's say via some simulation. So pulse width modulation is interesting because we can basically build a DAC, and all we really need is a low-pass filter. And we need a way to control the pulse width for a given signal. And once we have something like that, the precision with which we can adjust the duty cycle will dictate just how much precision we have in our digital to analog converter. So here comes the pulse width modulation cycle, and what we have is on time over total cycle time, and then we have times 5 volts, and then that allows us to approximate voltages that range from 0 to 5 volts with good decimal precision. So we've got several PWM circuits built into the pins on pins 3, 5, 6, 9, 10, and 11. And here they are, 3, 5, 6, 9, 10, and 11. These are all PWM pins. We can use them in other ways, but if we want PWM, this is the convenient way to do it because there's an internal timer that can be output directly to these pins. It's wired. So here's a thing called a light theremin, and what this does is it translates motion into sound. And what we've got here is a little speaker, which is being driven by an input from pin 4, and then its output goes right through this resistor that current limits things. There's the other side of this is a ground. And then for the analog input, what we've done is we've used a cadmium disulfide photocell, and that has a different resistance for different amounts of light. And so we can wave our hands in front of this, and it can be used to create a so-called voltage divider. So this yellow output goes into the analog input, and it can range between ground and 5 volts, depending on how much light is being shown into the photocell. So putting a 330 ohm resistor and an LED on pin 9, that's going to do some kind of current limiting. Probably the current will be something on the order of 5 divided by 330, which would be 15 milliamps. Limiting the amount of power that these things take is actually a reasonably good idea, not just to salvage the LED, but to allow power to be used for other things. Because if you've got too much power being drawn, other things will no longer function properly. So here's a mechanism for doing serial communication, and we use our USB interface for that. And so the USB interface is effectively a means by which we transmit and receive serial data. And we say it's serial because we take the bits and we send them out one bit at a time. And if it were parallel, we'd send out multiple bits at the same time, but we don't do that. So I only need a single wire to send data and or receive data. So if I want to upload a program through USB, typically what happens is I start to see the transmit and receive lights blinking. And if I open up the serial monitor, this is where I get an opportunity to take serial data and output it to my console. And that is very important for debugging. And this is something that I think everybody here needs to know how to do. So the Hello World program for the Arduino has to set up a baud rate and output data directly through the serial port, and using the USB form factor, come up into the console of the Arduino IDE. So here's some ways you can do that. I've got a serial begin, and I can put in a number like 9600 baud. Then I have a serial print, which can allow for a new line using serial.println, or no new line, serial.print. And so I can look for serial data using a serial.read, and that data can come in from the Arduino. And then I can check to see if there's serial data available. And then I can write serial data to the Arduino and or parse integers from the console. So that's very cool. Let's see if we can open this up. Oh, having a little trouble finding that one. So we'll do an example of that for the lab. We'll have an opportunity to do some serial I/O through through Tinkercad. We can use Tinkercad as a nice and easy to use example for serial I/O. So communication protocols that exist, there's the serial TTL, and what that does is it enables us to communicate directly to shift registers in TTL, that is transistor logic, or we can do serial communication through the USB interface. The USB protocol effectively gives us two differential voltages, the original signal and then the inverse signal. And that's because it gives us a chance to transmit so-called balanced signals. And balanced signals, what we do is if there's interference, we can take the original signal and then subtract off the negative of the original signal. And if there's interference on the original signal, it's D plus I. And we can actually draw that out. Let's see if we can do this. We'll do a pen. So here's what happens. You get D plus. It's so hard to draw on this. And then you have another signal called D minus. And this goes into an op amp. And it says plus, and it says minus. And then somewhere in here, we've got interference. So it's D plus the interference. And here's minus D plus interference. When you subtract minus D plus interference, you get the original D with negative interference, and that cancels the interference out on the positive leg, and what comes out is twice the original signal with no interference. And that's called balanced digital transmission. So that's kind of cool, actually. And that's a nice way in which to make the USB transmission, we'll call it noise robust or noise immune. So here's a class we can do. Here's an exercise we can do. Serial.parseInt, and that'll read a numeric keyboard input as an integer. And maybe we could do that real quick. Let's see how many of these exercises we have. So what we'll do is we'll bring up the Arduino IDE, and at the same time we'll bring up Tinkercad. Okay. And we'll create a circuit. And what we'll do is we'll try some really simple serial interface. So let's try new circuit. And we'll find an Arduino. And then what we'll do is we'll create some code using text. And then we'll do serial.begin (9600), and then we'll do serial.println hello world. And now, if we start simulation, we can go to the serial monitor, and we can see it's printing hello world in a loop. And that's basic serial I/O. That's it. That's the whole thing. So let's stop the simulation for now. And now, let's go back to our little PowerPoint presentation and see what happens if we do serial.parseInt. Right? So we go back to our hello world, and we say, please enter an int. And what they'll do is we'll say serial.parseInt. And that'll return an int. And then what we'll do is we'll print it. See if that works. So it says, please enter an int. I'll put in 99 and hit enter. And he came up with 99. Let's try another one. 100. And he outputs 100. So that seems to work reasonably well. Let's stop the simulation. And so that gives us an idea of how we can do some kind of basic I/O with the serial port. And that's what I have for you for today. Hope you liked my little presentation. Thanks a bunch. Bye.